Good morning, all. Welcome to my channel, Data Analytics, from theory to practice. Then we'll be talking about K-fold cross-validation today. Now, in this lecture, expect K-fold cross-validation demystified. Now, let's take an example. Let's say we have a data set containing 1,000 data points, and we want to split the data set into 80% for training and 20% for test. Now, let's take an example of a student who has 800 questions to practice, and at the end of the day, the student is being tested using the 800 question pool of questions, and the student perform well, excellently well, say 100%, 90%, because there's a continuous use of those questions. Now, when in a case where an unseen questions came or is being set for the student, and the student score low marks, this 15% or 20%. What that means is that the student is familiar with those questions, with the questions is used to practice. So by implication, as we train continuously on the training set, bias increases. The student could not evaluate him or herself very well because it believes that questions, test questions, exam questions will be limited to those 800 questions it's been practicing. Therefore, and that is why we need cross-validation in order to avoid such errors. And when we look at when such happens, our model may be inconsistent and unreliable. Now let's look at what cross-validation does. Cross-validation is defined as a statistical method used in machine learning to evaluate the performance of a model by definition. Then what cross-validation does is primarily used to assess how well a machine learning model generalizes the unseen data. It also involves splitting the data set into multiple subsets where the model is trained on one portion of the data and tested on another. Why use cross-validation? Number one is to reduce overfitting. As in the case of that student, it performs very well in the training set, but when it comes to the testing, the unseen data, the unseen tests, the unseen questions perform poorly. And that is why there's need to have multiple subsets. Okay, now it makes better use of limited data. It also helps performance estimation. It helps in model selection and hyperparameter tuning. Now let's look at the procedure involved in conducting K-fold cross-validation. Number one is to split the data into K subset or fold. The next thing is to, for every I goes from 1 to K, train the model on every fold except height fold. Then compute the test error on the height fold and average the test errors. Now we have, for each, assuming we have 5 folds, we are going to conduct the average. Now let's see what it looks like for K-fold cross-validation. The first iteration is, like I said earlier, if we have 5 folds, for instance, the first iteration is to test on the first fold and train on the remaining 4 folds. Then in the second iteration, we leave the first fold. Then we test on the second and the 3 others. And the iteration goes on and on. Now let's look at an example, a numerical example of k-fold cross-validation. Let's have a data set, 21 up to 13, that's 15 data point. So what we do is we divide the data into k equally sized folds, or we subset. Then the model is trained on k minus 1 fold and tested on the remaining folds. Then we repeat the process k times, with each fold serving as test once. Then when we look at that, we have 15 over 5. Since we are dealing with 5 folds, we have 3. So each fold, we have 3 elements. So we have K1, K2, K3 up to K5, and the folds are arranged the way the data is arranged, just like we have on the picture earlier. Now let's look at in the case of unshuffled folds. If the data point is not shuffled, this is what we have. We train on 14, 15, 18, up to 13. Then we test on the first 3. Then the second fold, we test on the next 3 and train on the remaining data point. Now let's look at, should we have an error, test error from each fold? Each fold, when we use our data on our model, the data will obviously give us error, maybe root mean square error or whatever error you want to use. Then we have, for instance, the error in K1 is 15, the MSC error in K2 is 12, MSC error in K3 is 8, K4 11, and K5 9. So what we do is to average this error and come up with the cross-validation error. Now, assuming we just generalize and pick and just do it once, and we obtain 15. And we say, okay, we say 15 is our error. That would be tantamount to committing a blunder, which result to overfitting. Now let's take an example. This actually, the data was subjected to analysis in Python, and this is what we obtain. The train MAE, that is mean absolute error for ARIMA, is 6.17, and for AMA is 5.51, which is lower. The train RMSC root mean square error for ARIMA is 6.80, while for AMA is 6.14. The text MAE for ARIMA is 17.63, for AMA 11.45. Test RMSC for ARIMA 18.03, AMA 12.27. We can see that AMA performed better based on training and testing error values. So now, what that tells us is that that particular data shouldn't have been subjected to ARIMA. It is better subjected to AMA. And we have been able to establish that based on cross-validation. So the ARIMA model has significantly higher test error, which suggests potential overfitting, or that integrated at the differencing component may not be needed for the data. Then the forecasted values for ARIMA is around 25 to 26, which seems to be consistent, but considering the high test error, those forecasts may not be reliable. And we can reduce the variance in our model by doing what? By adding bias. We increase bias in our model to actually reduce variance, and that is what regularization does. And a model with less variance is more efficient among other models. So with this lecture, I believe you have been equipped with what k-fold cross-validation is. And stay tuned, subscribe to my channel, and so that you can have access to more videos. Thank you.